in the chat, but now we can move on to our next speaker. So can you please call the next speaker? So our next speaker is Dr. Noor Yuziah Mohd Yunus. Her presentation is processing and alkali treatment impact towards oil palm frond fibers bulk, density, and wood plastic composite performance. Dr. Yuziah, can you please join us?
Dr. Yuziah, are you here?
Yes.
Thank you.
Okay. I want to share my screen. Assalamualaikum and good day to everyone. I won't say evening because we are evening here, but the rest are just starting your day. Okay, and just let me introduce.
Can you please go to full
yes.
screen mode?
Can you hear me?
Yes. Can you just go to full screen mode?
Yeah. Okay. Okay, done.
Yes, perfect.
Okay, so for this paper, it's a combination of me, Nur Farhana Jasmi. Actually, it's the work of Nur Farhana for her PhD, and the co-supervisor, Wan Muhammad Nazri. And I'm just taking a small snippets of what she have done, and just to share some information there. Okay, so what I'm going to do is just to give you a very simple introduction and what work is done and the conclusion for that particular section of the work that she did. So here I share with you a bit on the pictures that we have for our oil palm. So we look at the plantation, the individual plant, and then you look at the bottom there, the plant with the products that we get out of this. Okay, and I believe since this is on the third day, you would have seen a few more of this. Okay, and I said thank you to Dr. Nurul for actually introducing quite a bit of things just now at the beginning. So I'll just basically go into the products that we are actually working with now. Okay, so the players for this particular study is basically the oil palm frond, okay, which is basically what's being used by Noor Afifah. And then we work with plastic. We actually choose the normal plastic, what I call the indicator plastic, which shows the industrial material that's being used. And then the plastic that we choose is polypropylene. I actually short form it there. And and basically it is a material that is actually stable when we actually use it outside, because you will get UV irradiation and stuff like that, and we want to have actually material that is stable. Now in just now we were looking at our palm trunk. Our palm trunk, admittedly, there is a lot of material there, and you're looking at just last year 106,000 being replanted. So you just imagine there is actually about 50 million metric ton of material they actually are working with. Now, oil palm frond, why it is very something that we want to actually look at. One, when it was studied earlier, this particular material is actually very, very close to wood material, what we call a tropical wood in terms of the fiber property, and in terms of what we call the buffer capacity or the behavior of this material against what is currently what material is currently used in forming products such as particle board, MDF, and so on. So working on that, we work on our palm frond, and we get a lot of this. For every tree, every year, every tree will actually produce about 82 kilogram of this material. And you're looking at 140 trees per hectare. And in Malaysia, you're looking at a volume of 42,000 hectares of stuff. So it come out to be quite a lot of material that we can actually work with. So when we work with this, we actually come together and we actually produce what we call the WPC, or the wood plastic composite, where we actually try to marry wood and plastic, which actually will give you a very strained relationship, because we know we are having something that is hydrophobic and hydrophilic to be put together. So main issue, we have compatibility issue. So what happened is, because of this compatibility issue, we actually work towards surface processing. And the surface processing that we actually decide to go with is just the utilization of sodium hydroxide, which is a simple material being used in our pulp and paper industry, cheap. And if you actually can work with this, you will come up with a product that is easily produced using material that is common. Okay, what we call a common material in the industry. So when we do this, we actually have to do, we have to restudy back the fiber, the material that we actually obtain. So when we restudy this thing, we have to look at things like chemical content and what happened to the bulk density of the material at the end of the process. Because once you change the chemical content, once you change the bulk density, it will give you different ways or different methods that you need to consider when you are processing them. So we treat this with sodium hydroxide, 1%, 2%, and 4%. And I will actually show you the result of this particular test. But later on, when we actually do the production, we decided to actually just work with the 2 and 4% because of the differential that we actually see in the properties that we observe. So the product, the fiber, the particles that we actually treat, we go to the next stage. We do wood plastic composite. It's very simple, just the plastic being put into the blender, and then we add in our fiber, and then we actually just mix them together. Temperature used is 180 degrees C, and the timing we actually estimate about 40 minutes for all. Now, the timing is a bit longer. If you actually look at the work done, a lot of timing is very, very short. And that's because they actually are working in very, very small volume. They're looking at volume of 50 grams, 120 grams. But we are actually looking at a volume of about 1.5 kg, which is actually a lot of fiber to be made. Okay, so this poor student actually have to come up with a lot of fiber to come up with all the combination. So, and then what we do is we look at two loads, 10% fiber inside the plastic and 50% fiber inside the plastic. And both of them will actually show you what happened when you when the matrix is a lot and the matrix is less, and what would be the properties that come out of this. After that, we just do flexural, tensile, impact, and water absorption test. Okay, so after going through all that and doing the test and looking at this, I suddenly realized we missed something. Okay, we look at the cold water solubles. Okay, once we do the treatment, we find that immediately the cold water soluble drop. Okay, drop because the sodium hydroxide is effective enough to actually take off a lot of the sugar contents, the simple extractive inside there. And then we find that with the hot water soluble, again, you see that type of major drop. But interestingly, towards the end here, you find that at 4%, it's not really, it's not really what you call giving you a complete drop. So it's just a slight increase in there. Actually, I'm still trying to figure out why it does that. There's a lot of chemistry that goes into this, because sometimes when you want to remove something, you have to be very careful, because you will remove at certain concentration, But after certain concentration, you actually have a negative reaction. So there is a chemistry behind this. I'll have to work on why that happened. Okay, so but what this says is, if we were to do this processing of the material, don't go overboard. Just go for about 1 to 2%, and that should be good enough for you to actually clean up your fiber for the process. And then we have our alcohol-tolerant content, and we find that the alcohol-tolerant content is actually going down. So it is something to do with something that is hydrophobic in nature, that is actually will be taken off with the sodium hydroxide addition, which is very interesting. And then the lignin content is going down as it goes, because the sodium hydroxide will actually partially dissolve them, and the H content is actually going up. This is actually, I believe, the sodium hydroxide is now actually going back and becoming attached by a slightly strong bond, so that it actually get captured into the ash, ashing of the material. Okay, the bulk density wise, we actually look at different sizes when we do bulk densities, and basically the bulk density will actually go down, okay, as you actually remove the ash, and for the smaller particles, but for the bigger one, it actually have a slight reverse. So this is actually, if you look at this pattern is actually quite similar to the pattern that we have up there, the one before this. And because this result is actually a combination of all the three. So we actually see the stronger effect where you actually have a slight increase in bulk density. So again, I believe the sodium hydroxide actually have changed some crystallinity inside the structure, causing it to have a slightly different bulk density. But all in all, you can see that once you do this treatment, the bulk density will actually drop, which means when you do processing, you have to be extra careful because it's a lot harder to handle. The lighter the material, the harder it is to actually form a board, for example. Okay, so this is what happened with the profile. You have seen just now clean material without any treatment. So this is a closer version. Just now, I think the magnification is not this high. So when you magnify it, you can see that these are the block part, the block pores when you have without the treatment, and with the treatment, you can actually open the pores. And open pore, everybody know, you increase surface area, you can actually do a lot of things when you want to do interaction of the material. So that's what we actually have managed to get. So in terms of flexural, in terms of flexural, we only now look at 0, 2, and 4%. For bending, we find that the bending is actually the interesting part is because remember the value that you see at 4% is actually going up for your co-water soluble and so on. It's interesting that you actually have a U shape. You actually have a U shape, and you find that in terms of the modulus itself, I speak Malay suddenly. In terms of the modulus, you find that the modulus is actually getting stiffer. Okay, and it shows that there is something being caught when you actually use too much sodium hydroxide when you do treatment. So this is for 10%. In 10%, you don't see the impact so well, but when you look at for 10 and 50%, in terms of modulus of rupture, the way it breaks doesn't make much difference. But in terms of modulus of elasticity, you find that the 50% is actually higher in terms of modulus of elasticity. And then for tensile, which is actually just the pulling, we actually pull this thing apart. When you look at the tensile, you find that the tensile is actually, of course, stronger with the 10% because we are now measuring more the plastic rather than for fiber. Once you add in the fiber, you find that the tensile is actually going down. And the modulus of elasticity is actually stronger with the fiber, which is interesting, even though it breaks easily, but it is actually more flexible. Okay, even though it breaks easily, it is more flexible. And in terms of elongation in break, you find that there is longer elongation when you use the 10% fiber inside your wood plastic composite. And the higher the loading, this is logical. It will actually be able to break faster, and therefore it will not, because it could not elongate that easily. Okay, impact. For the 10%, your impact is actually lower compared to the 40% loading. And basically, when you do impact, you want to see how well the stress is distributed. And when you have fiber in there, you find that when it hits the fiber, when it starts to break, when you hit the fiber, it will actually have many layers for you to break. Whereas when you have more plastic, the part in which you have the plastic matrix, when you break, it actually will break more faster, and then you do not have a material that remove the stress. So you find that in terms of impact, you will have better impact performance when it comes to when you do fiber. In fact, when you do impact, you notice that when you do the test, the way it breaks, it shatters completely when you actually use very low fiber content, which is very interesting also. Okay, water absorption, this is expected. If the water absorption is less for 50%, I would actually like to know what happened to that product. Okay, so there is more water absorption when you have more fibers because of capillary. I know I actually have another 3 minutes.
Yes.
I put my timer on. Sorry.
No, thank you. I just wanted to give a.
Okay, so conclusion-wise, so I know I always put a timer on my side. So it's very abnormal for me to go over time. Okay, in terms of sodium hydroxide treatment, it have the impact on the chemical composition. Basically, indirectly proportional. You find that when you put in the soda, it will actually remove, therefore it becomes lower. However, it cleans the fiber, it generates good surface property, and it gives you actually lower bulk density because of the presence of the void. And when you look at the composite, it has positive result when you do the treatment, and the result is positive for every single processes that you actually look at. And for this particular test, the loading, we show that when you have higher metric contents, you have a different performance compared to lower metric contents. And it depends on what you want to use it for. If you want to use molding, for example, then you go for material with high metric contents, which means PP is high. Or if you want to go for something like furniture, structures, and so on, it is an advantage for you to go for the lower, for the higher filler content or fiber content. So I stop at that. I just shared a bit of nice picture here with you, enticing you all to come to Malaysia. Okay, thank you.
Thank you very much, Dr. Yuziah, for your nice presentation. And for the Q&A question, I would like to have maybe 1 or 2 questions from the audience.
Okay, I stop first dismiss first my timer. Okay,
if I may ask a few questions. So first of all, I would like to thank you for this very good presentation. It's it's very close to my personal research. We're doing research on date palm fronds, and we're doing extracting textile fibers from the frond stalks, and it was quite interesting to see because it's often when we look at research done on oil palm fiber-based products, they are often from either the trunk or from the empty fruit bunches, but much less research is performed on the fronds. So this is something that was really new to me. And I wanted to ask you a few questions. The first question, you have shown the morphological features of the fibers, but the longitudinal features, and you have shown those particles, silica particles on the surface. But what about the cross-sectional shape of the fiber? Are they like vascular bundles, or pure fiber bundles? So this is my first question. My second question is related to the impact testing. Did you try to do like a pendulum impact or a drop weight impact testing? So this is the second question. I mean, I would just go for those two questions to allow more time for other questions from other participants. So like related to the cross section as well as the type of impact test performed.
Okay, just a quick one. For the impact testing, we did a pendulum test. So it's just a simple, it's not even notch. Okay, it's not even notch. So it's just a simple cut sample and then a pendulum test, because you can actually have both notch and unnotch, but that's it. But when it comes to the fiber, when you actually do a cross section of the fiber, you will actually see them as if you are looking at small dots. Okay, yeah, you can actually see individual fiber out of them. And that's part of the reason why Dr. Nurul can actually slice them up to actually give you that material that you can actually do matting. Okay, you can actually wove them together. So it is almost like looking, when you look at papyrus, for example, where you cut it, you actually have that long fiber for the movement of the water. So that's basically what you'll be looking at. So if you cut it the other side, you can actually see all these parts. In fact, yesterday there was another, I was at another seminar. It actually showed that picture of the way it is when it's actually cut across. I can't hear you.
Thank you so much. I think Professor Kais also has a question.
Dr. Madia, for this nice presentation and to chat your achievement. My question is about the matrix. Use the PP as a polymer matrix to produce your wood plastic composites. How about the rheological properties of the both of the PP and the produced materials? There is some specific viscosity which is mandatory, or the melt flow index for the PP, or we can choose the PP injection grade or extrusion grade. They are the same.
Okay. The one that is being used here, we are using the mat flow index of 12. We are using mat flow index of 12. So normally, if you want just to do normal type of blending, where you are not going to do radiation and so on, you go for 12, between 12 to 15. The reason is because if you have a very good bra bender machine, you can actually deal with something with lower melt flow index. Because first you see it melting, but the moment the fiber heat, it will cease. It will actually, the torque will actually shoot up. So even if you start with a torque that is 10, it will shoot up to something like 100, 150. So you have to be very careful on that one. So if your plastic is too, the melt flow index is too low, you might have a problem. That is if you want to do what we call conventional blending, which means you are not going to do any irradiation. But if you want to do radiation together, which is what I have actually done that, you should use something like 7, between 5 to 7 melt flow index. The reason is because the moment you hit it by electron beam, it will actually drop the melt flow index. So it depends on what you want to use it for. And normally in production, if you see the production that they do nowadays for wood plastic composite, they are looking at melt flow index between 10 to 12, which is very, very common if you do this product, and then they will come up with about 60%, 70% fiber inside there.
Thank you very much.
So we still have 2 more minutes before our next speaker. So anyone else has any questions? So perhaps I wanted to ask about like the sample preparation. So you did the compounding, and did you do afterwards like extrusion or compression molding to prepare the sample?
After we have prepared the sample, we actually break it down into a smaller pellet form. And when we do the board itself, we actually measure the amount into a mold and press it. We do have the capability to do extrusion, but for this particular test, we just want a flat surface. But of course, if you want to actually show whether this product is workable or not, then it works just like a normal extrusion plastic material, plastic pellets for extrusion.
Okay.
So it just depends on what you want to test it for.
Yeah, sure. Thank you so much. So